Nuclear energy, one binding energy. So the first video about nuclear energy. Now, if particles are attracted to each other, for example, just a proton and an electron, or particles and nucleus, then they are in a bound system, and to separate them you would have to do work, and the work you would have to do is called the binding energy of the system. So a nucleus is a bound system. The particles can't go anywhere on their own. You would have to do work to separate them all, and that work is called the binding energy of the nucleus. And strictly speaking, it's a negative quantity. It's not like the nucleus has this energy. It's the energy you would have to give it to separate all of the particles. Okay, how do we work out binding energy? Well, look at this. We've got proton, neutron, electron. We've got their masses, the mass of the free particles in atomic mass units. And let's calculate what the mass of a helium atom should be. And the mass of a helium atom should be, just add all of them up and multiply by 2, and you should get that, 4.032978 atomic mass units. What is the mass of a helium atom? Well, it's actually that. It's a bit less than that. So the mass of the whole atom is less than the mass of its bits. Why? And the answer is because the two systems, here we have two systems, the bound system and the free particles, and the free particles have more energy. Because we would have to do work to pull the atom apart, to get from left to right, you would have to do work. So the system on the right has more energy, and because that system has more energy, it has a bigger mass. And using E equals mc squared, or E equals delta mc squared, because it's the difference in mass, we can work out the difference in energy, and that tells us the binding energy of the nucleus. And you can do this yourself if you change U to kilograms and then do E equals mc squared, then change it to electron volts. You should get 28.4 mega electron volts is the binding energy of a helium atom. Note that nearly all of this binding energy is the binding energy of the nucleus. The work needed to take the electrons away is tiny. It's, about 10 electron volts. It's not a great deal at all. The mega electron volts is pulling the nucleus to bits because you have to overcome the strong nuclear force. So the binding energy of the atom is just about all the binding energy of the nucleus. Here's one for you to do. Pardon me. And I'll show the answer in 1, 2, 3. And there's the answer. You should have got 198.1 mega electron volts. Now, we can work out the binding energy of atoms from their mass. And obviously larger atoms will have larger binding energies because there are more particles to pull apart. So the binding energy of an atom on its own isn't that interesting. What is much more interesting is the binding energy per nucleon. So if you like, it's the binding energy of the atom divided by the number of particles in the nucleus. And that's interesting because it tells us what the stability of the nucleus is. If you have to do more work to pull each particle away from the nucleus, then it is more stable. It's in a deeper potential well. On that diagram, the diagram on the right represents a more stable nucleus. Okay, and this leads us to a very important graph. We'll have a quick look at it now, and then we'll talk about it a lot in the next couple of videos. And it's a graph of binding energy per nucleon against mass number, against nucleon number. And it's a very characteristic shape. Very often you'll see this graph where the binding energy per nucleon is a positive quantity. Just imagine that upside down. Usually on the OCR paper it is as it is here, and quite correctly actually. So look at it, and what patterns can you see? What is the most stable isotope?